Hi, this is the eighth lecture for the digital logic class where we discuss the combinational logic, um, adder, and magnitude comparator. Probably we'll start with the adder and then move on to the comparator. The most important thing about adders, I will be using the Paint tool for some examples, but I just want to make sure that we capture the most important aspect for adders. And basically, if I may use the paint tool here, um, the adders can be um, classified to half adder and full adder. And those are the adders that add one bit, one single bit. Um, the the full adder and the half adder basically differ in the number of inputs they use. So you can see if I draw a block diagram of the half adder, um, we have here two inputs. Um, one is the one of those inputs is the, let's say for example, A, and the other input is B, and the output is sum and the carry out. In the case of the full adder, though, we will have three inputs, A, B, and C, and we'll have um, the sum and the C out. Observe the difference here, where it is right here where we differentiate the full adder from the half adder. The full adder includes a third input. So you have here three inputs, while in the half adder you have two inputs. Both share the sum and the out for the full adder and for the full adder and the half adder. If we go back here to the presentation, we'll see that the um, the half adder truth table, um, you can see here, um, we'll use the highlighter. The half adder full table is that consists of the combinations for the inputs. In this case, my inputs instead of A and B, they are X and Y. And since I have two inputs, I have 2 to the 2 equal 4 combinations. And you can see that in the case of the sum, whenever I have a single one, uh, a single one for the input. So you see here 1, 1. In this case, you will have an output of 1 for the sum. While if you have two zeros or two ones for the x and the y, you will have the output sum as 0. In the case of um, the carry, you can see that the carry is 1 only when both x and y are ones, when both inputs are ones. If we take this to the design, we can use the K-map to do the simplification and draw the combination logic. And obviously, we have taken this in the previous lecture, and you will end up with the carry being uh, equal to x and y, and the sum is the exclusive OR of x and y, which is xy prime or x prime y. And here is the drawing where you can see that um, the let's just get the pen here straight. You can see the drawing of the carry right here, okay, which corresponds to this equation, and you can see the drawing of the sum circuit here, which corresponds to this equation right here. We can always abbreviate the drawing by using the XOR, okay, either in the drawing or the XOR in the logic, as illustrated here. Keep in mind, though, that this abbreviation in the drawing or in the expression does not reduce uh, the size of the circuit. Is just merely a abbreviated form. If we move on to the full adder, you will see that the full adder has 3 inputs, as we stated earlier, and 2 outputs. And the combinations for the inputs are 2 to the power number of inputs, 2 to 3, which is equal 8. As you can see, there are 8 combinations here, um, as illustrated here. Now, we can see that for um, for the sum, the output equals 1 whenever I have odd number of ones, very clearly. Whereas for the carry, it is equal to 1 wherever I have 2 or more ones in the inputs. We can take these two functions to the um, K-maps and simplify them and draw the logic, and we end up with this K-map. So this is the sum here. And in this case, notice how these ones are distributed in such a way that they are not neighbors to each other, and they can be simplified. While the carry is we are this it's a little better because you can see there are these 4 ones here can be merged into um, 3 simplified terms. Okay, uh, the, the sum here actually it is can be expressed as x exclusive or y exclusive or z. This is an abbreviated way to express it, but the hardware is not simplified. Okay, so let's continue here, and we can see that the drawing for the sum consists of the 4 terms in the K-map that we could not simplify, and the 3 for the carry, the 3 simplified forms that we came up with the K-map and with the OR gate at the second level. So you can see that, for instance, let's suppose if I am adding 1, 1, 1, okay, into a full adder, and this is x equals 1, y equals 1, and z equal 1, you would end up with a sum of a 1 and a carry of a 1. That's what we expect. Now let's take a look and see how the hardware does deal with it. So x here is 0, x prime is 0 because x is 1, y prime is 0, and y is, and z is 1. So therefore the output here is 0. 0, 1, 0, the output is 0. 1, 0, 0, and the output is 0, 1, 1, 1, and the output is 1. So you have this now XOR, which is fed 0, 1, 0, 0, sorry, 0 and 1, and therefore the output is 1. Similarly, we can look here at the input for the carry, where you have the x as 1, y 1, 1, 1, 1, 1. So you have 1, 1, 1, and the output here is 1. And this is what we have predicted um, earlier. And this is the carry here. What we have predicted earlier uh, was executed by the designed circuits. Okay, if I move on with the slides here. Um, Now, one thing we can do here is to design a full adder using half adders. So this here is half adder, and this here is also a half adder. And the question here comes in typically as design something using something else, and this is like me saying design an oval shape using a circle. Okay, well, someone can start with the circle and then stretch the circle out, and then until you get this oval shape. And this is typically these type of questions. If I was successful to abstract the idea, you are asked to design something using something, and that something is already designed for you. You don't need to go down to the logical gates, and most of the times you don't really need to use K-maps. And in this case, you have to be clever into understanding the larger design, the larger design. Oops, I did a mistake here. Let's see, the larger design and the small design. And you have to understand their functions so that you can compose the larger design using those smaller blocks. And in this case, we understand that if we use a half adder, the output, the sum here, is the XORing of the first two inputs, okay, which is X and Y. And I know that the carry is X ANDed with Y. And then when I get the output of the sum of the first half adder, which is this one, with the third input here, which is the Z here, okay, then I can generate X or Y, I'm sorry, exclusive or Y, which is an input, exclusive or the third input here, which is Z, using the second half adder, and this is coming from the sum input of the second half adder. And also I'm going to get another carry here, which is X X or Y ANDed with Z. And it turned out that you can really generate the carry of the entire circuit, which is a full adder, by just ORing the first carry, which is right here, and the second carry, the fresh carry that we generated of the second half adder. So really, um, uh, 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 I would say those for us, for the most part, are black boxes here, and people in many of these situations are not interested in the details, and you really need to just design the full adder using the half adder, two half adders, and an OR gate. And with that said, we can always move now from just designing a single bit to multiple bits. And in this instance, we are adding two numbers, A and B, where A is 4 bits and similarly B is 4 bits. And so you can see that A here consists of A0, A1, A2, and A3. These are 4 bits. And similarly B consists of B0, B1, B2, and B3. So the question is what we were doing before. Well, what we were doing before really is we were just adding a single bit to a single bit, and so we really were adding two numbers, but every one of them is just a single bit. And now we are expanding this to adding two numbers as well, but every number of those is 4 bits. And for that now we need to, to, to use full adder for every bit position here. For bit position 0, we need a full adder. For bit position 1, we need a full adder. Bit position 2, full adder. Bit position 3, full adder. And the way we'll connect them is as follows. So this is the full adder for bit position 0. And this is the full adder for bit position 1. This is the full adder for bit position 2. And this is the full adder for bit position 3. And now notice that how we are connecting those inputs. So for the two inputs here for this full adder, we will add A0, B0. Similarly, for the two inputs for the other full adder, we'll add A1 to B1 because these are of equal weights, and A2 to B2 and A3 to B3. Then notice that we have a carry which goes into the first full adder, okay? And this is typically for an addition will be a 0. And we'll see that in the case of subtraction will be a 1, but for now this is just so it's a 0. So you can see here these are my three inputs. And obviously I'll have the sum, which is of the bit 0, and I'll have the carry, which is C1 here, that is going to the next bit position. That's our carry out that we used in our mathematics in elementary school. Whenever we add two numbers in digit position, so the carry out will move them to the next position. Because the carry out weight is higher, we cannot add it here. We have to add it to the next bit position. So now we are adding B1, A1, and C1, and generating sum 1 and carry 2, which goes to the next bit position. And then in the next bit full adder 2, we'll add C2, A2, B2, and generate sum 2 and C3. And similarly, we'll add A3, B3, and we'll generate sum 3 and carry 4, which is the carry of the entire circuit. And to verify, let's just assume, for example, that my numbers here, let's just say, for example, I want to add 1, 0, 0, 1, okay, that's my A, to 1, 1, 0, let's just say another 1 here. Okay, so you can see here that the A here is 1, 0, 0, 1, that's for the A, and the B, it is 1, okay, and 1, all right, and 0, and another 1. Let's just assume for here that the carry in is 0. So now we are adding 1 plus 0, obviously a sum of a 0, and then I have a carry of a 1. And this carry moves into the next stage, and where I'm adding 1, 0, 1, I have a sum of a 0 and a carry of a 1 that goes to the next stage. Now, notice in the next stage, I'm adding 1, 0, 0. So that's a sum of a 1 and a carry of a 0 to the next stage. And here I'm going to have a sum of a 0 and a carry of a 1. So now you can see that my output is 0, 0, 1, 0, and a carry of a 1. So that's my result of this circuit. Okay, I'm going to differentiate this carry here. Let's double check our math here. 1 plus 1, 0, okay, 0, 1, 0, and a carry out of 1, which matches what I just got down here in this example. Okay, so this is in terms of 4-bit. Now, obviously, one question is about the delay of this adder, and the delay of this adder is important because these type of adders are carry propagate adder, and their delay basically I'm sorry, their delay basically is not, they don't produce the sum in the same time. First of all, we produce this adder result, then this adder result, then this adder result, then this adder result. So you can see that the delay or the propagation delay of this of the circuit is equal to the number of bit position, which is in case 4, times the delay of every individual full adder. So for instance, for example, let's just say every full adder takes, for example, 1 nanosecond. For example, so the delay for this 4-bit will be 4 times, oops, wait, that's too quick. Okay, it'll be 4 times, let's just, sorry about this, snafu, 4 times 1 nanosecond, because every stage will take 1 nanosecond. With this, I'm going to conclude the first part of this lecture, and we'll continue the discussion with the second part